So we have Mortaza speaking about applied control theory.
Thank you for introduction. This is the second talk on applied control theory. In the previous talk, we introduced the applied control theory and we introduced different control systems, and we showed that why we need the feedback control system. We compared the result for the open control system and closed control system, and we show that why do we need to have the feedback control or closed system. And we show the utilities of the closed control system. The first utility was in terms of the uncertainty. We showed that the open loop control system are not efficient. So we show that we need to actually to have the closed control system. So because the reality has uncertainties. First utility of the feedback control is to show the actually the preference to the open loop control system. And we discussed that when we have, for example, the external disturbances to the system, here you see that the TD is the disturbance to the system. And then we compared if we have such a disturbance, is open loop control or closed loop, which is much better. And we compared the result by the simulation. So at the end of the story, here this figure shows that if you have a rotating this speed simulation under different assumption, okay, so when there is uncertainty, actually the open control system cannot catch and reach to the expected, speed that is set prior. So we need to control for this uncertainty in the system. So we define two types of the control feedbacks. One was an extreme feedback. The extreme feedback says that, okay, if the actual speed of the disk is different from the actual speed is different from the expected, so there is an error. So the control system will set the torque to the maximum when E is greater than 0, and when E is less than 0, it will set to the minus T max. So this is two extreme cases, okay? So, and in this case, we will see that what will happen if we have such a feedback to the control. So our first of all, we measure the speed by the sensor, and in this system you see that there is no estimator because this is a simplified system. So we have just the sensor. Sensor verifies that the actual is equal to the feedback speed and sends to the controller. So because there is a deviation, it means that the expected speed is not equal to actual, or actual is not equal to expected, is much better to say. Then the controller revises the signals and send the signals to the actuator. So in both those cases that we mentioned, if E is greater than 0, it will send the signal and set the torque speed to the T max, and if E is less than, it will be set to minus T max. So, and then it will be sent to the torque, and then the process will receive that in the case. Okay, so, and it will be continued. So if we have such a controller, the simulation result shows that we will reach to the expected speed, and it will be steady speed for the period of the simulation. Okay, so this is the first utility of the feedback control. So it means that in the case of the presence of uncertainty, the feedback control actually perform much better than the open loop control system. So, but you know that this extreme case, when there is E equal to 0 and switching from this, this will be sharp switching. So we can make a proportional feedback control to switch smoothly from both cases. Okay, so in this case, we can set the feedback rule as this one. If E, this is error, or the deviation of the speed from the expected speed is much more than the T max over P, okay? And P is a proportional, okay, coefficient that we will proportionally adjust actually the torque and the signals. So if it is greater than T over P, then it will set to the T max. And if it is less than minus T max over P, then the controller set the torque to the minus T max. And if it is between, then it will be proportional to the disturbance or the deviation of the speed. So it means that there will be a smooth transition, okay? So in this case, that we have, again, the system like this one, okay? So we have controller, process, and we have the sensor. Sensor measures the speed and verify that it is, for example, as a feedback control, the feedback speed, and send to the controller. Then the controller will process this one according to the law that we mentioned before. Okay, so it will be proportional. So then it will send to the actuator, and the actuator will affect the process, and the process speed will be measured again to reach to the expected speed. So to compare these two cases, in the previous one, the extreme case, as you see that if the actual speed is this different, E is greater than 0, the speed will be set to the T max, okay, the maximum speed of torque. And if it is negative, then it will be set to minus T max. So this is the extreme case. And this one shows the second one, the proportional one. As you see here, when around the E equal to 0, the transition will be smooth. So that was the first utility of the feedback control. The second utility, the question is that if there is no uncertainty, okay, is there any superior, is actually the feedback control superior to the open loop control or not? Because if there is no uncertainty, we show that in open loop, we can reach to the expected, but it takes time to reach the expected speed, okay? So in that case, maybe some people say, okay, when there is no uncertainty in system, we do not need the feedback control, and there is no superiority for the feedback control with respect to the open loop control system. So the answer is that although there is no uncertainty in the system, the time adjustment, the time that we reach to expected speed is much faster in the feedback control with respect to the open control. So this is the second utility of the feedback control. So it means that although we have no uncertainty, we can show that the speed or the speed of the expected speed will be reached so faster in feedback control. So to simulate that one, we use the same parameter and we assume that there is no disturbances here, okay? It means that there is no uncertainty and the parameters are fixed, okay, as before, the friction and inertia, all of them as before, and there is no uncertainty parameters. So we wanted to show that can feedback still outperform or the outperform on the open loop control system? So to this one, we again set the desired speed to v is equal to 1, and the other parameters as before, and simulate the result here. And so this is the result that we got. So as you see, in the open loop control system, okay, with no uncertainty, we will reach to expected speed, which was set to 1, but over time, it takes time to reach to the expected speed. But in the case of the closed loop, we will immediately or faster, at least faster than the open loop will reach to the expected. So in terms of the cost, sometimes the time is so important, and when the time to reach to the optimal or expected speed is important for the planner, okay, the closed loop outperforms with respect to the open loop control system. Okay, so this is the result that I got from the simulation, and we can simulate for different systems to show that outperformance of the closed loop control system with respect to the open loop when there is no uncertainty in the system. So this is called the second utility. So in conclusion, so even we have no uncertainty, both methods will reach to the expected speed, but the feedback control achieve faster response, okay? So, and then it will be smoother or stable, okay? So, however, there are some limitations for feedback control system. So, we show that the open loop control system does not perform in the case that there is uncertainty. Okay, and we show that even there is no uncertainty, the feedback control outperform with respect to the open loop. So, however, there are some limitation in the feedback control. Okay, so maybe here I raise this idea that the simulation result may result in that. Okay, so the feedback control is universal solution, but it is not the case. Okay, so as I use the proportional the feedback control to show the simulation result in the previous example. Okay, so in the case of the rotating disposition control, we will show that the feedback control does not perform perfectly. Okay, so the result will be unstable and there will be fluctuation. Okay, so in the previous case, our target was the speed. Okay, and we control for the expected speed. But the question is that if we change from the speed to the position of the disk, okay, then does the feedback control perform perfectly or not? Okay, so this is the question. So we will switch our problem to the position control, from the speed control to the position control. So our goal is to achieve desired position of the disk. Okay, so again, we assume that there is no uncertainty in the system. Okay, so according to the second utility, you know that we expect that feedback control perform good. Okay, so but we will show that in this system that we target the position. Okay, then we consider the position as well. So in the previous one, the target was expected velocity. So here we change to the position. So the performance here, the process shows that this is the performance of the disk, okay, the position of the disk. So we change that, we know that because v is the derivation of position to the time, so our equation, the differential equation, will be of the second degree of 2, so it will be j the second derivation of p with respect to time because of this the definition of the velocity. Okay, so our system is the same except that now we wanted to control over the position of the disk. So if we simulate and we set again our feedback proportional feedback control, this is our rule, as before, okay, it is proportional. So then again, we will see that here we have the controller. The controller, you set the torque speed according to this rule that we set. So, and send to the actuator, and actuator sends the affect the process, okay? So then the position of the rotating will be measured by the sensor, and we assume that again there is no estimator, and sensor estimator are simplified to each other. Then the position PF is the feedback position, which will be sent to the controller. Again, the controller will send the signals. Okay, so this is our system. So, but our simulation resolution, if we set the position, expected position equal to 1, okay, then although there is no uncertainty and we use the proportional feedback, we see that there will be oscillation in the position of the disk. Okay, so we see that the several transitional oscillation is undesirable, okay, and highlights the limitation of intuitive, sorry? Yeah, the oscillation will decrease, but it will not stabilize. As you know, that at the end, at the time of t even, the position will not converge to 1. Yeah, ever it will be oscillating, although the oscillation, the domain will decrease over time, but the oscillation generally is not desirable, okay, first of all. So it takes time to have the less oscillation, okay, so the oscillation will decrease, but even after 10 step of the time, it will not converge to the expected value, okay? So it means that if our system is of higher degree, then the feedback control will not be effective, okay? When we use the proportional. So what can we do? We can go further and adjust for this oscillation as well. How? You know, when we had the deviation from the expected value, for example, the speed, we use the proportional feedback to control for that disturbances, okay? So in this case that we will control for the position of the disk, so we see that it will oscillate, so we should use more derivation, okay, to control for the oscillation. So our solution for this one is to use actually this system here. I will get to previous slides. So this is the proportional derivative. It is called the proportional derivative feedback. This feedback has one step more, or there is one component more an extra to the previous proportional that controls for those oscillations, okay? So here our rule shows that if we have such a deviation, so you know that where this is the E actually is the deviation of the position from the expected position, and this will be equal to speed, okay, by definition, okay, because you know when you derive the E with respect to t will be the derivative of position is the speed, okay, and this is constant because it is the expected value, so that will be minus v, okay. So this is our rule. The new rule controls for the deviation of the position, okay? So it will control for any oscillation. So then what can we do? In this case, we will see that incorporating this term in our control, okay, will control for those oscillation, okay? So let's go to the result again. This is our system. So in this system, we have a derivation gain, which d is the derivation gain. It's a constant term, okay, like the proportional p that we had before. So, and as well, you see that our system will have a controller, a process, and a sensor. As you see here, the process is the position of the disk, explain the position. There is no uncertainty in the system. But here in the controller, you know the torque is a function of E that incorporates PE plus dDE with respect to T. So this derivation controls for the position of the disk. So, and D is the derivative gain coefficient. Okay? So our rule has been enhanced. So again, we will use the same parameters. J, B will be the same parameters, and we will simulate the system to find what will happen. So here we simulated the system for two values. We assume that there is the friction, okay? So, and we simulated, and the results show that if we set the expected position of the disk to 1, okay, then if we have the most updated version of the control rule, we will see that the system will stabilize, okay? So then the position will reach to expected position immediately, and it will be a steady, okay, for the forever. So, okay, so our results shows that this proportional derivative feedback outperformed to the proportional feedback, because in proportional feedback we had oscillation, but in this proportional derivative feedback there is no oscillation and the system will be stabilized, okay? So another question is that if we assume that there is no friction, so B is equal to 0, what will happen? So the result is simulated when there is no friction in the system, and we will see that the position will overshoot at the beginning and then will converge to the expected position. So yeah, what is the result? Because at the beginning, why we got this result? I mean that when there is no friction, as you see, the position of the system will overshoot, okay? It will be much higher than the expected, and then we'll get back because there is no friction, okay? And the system will adjust for the total deviation, okay? So, but when there is no friction, the momentum of this adjustment will be high. So then the signal that is sent to the actuator will affect the process, and then the position will be higher than the expected position. However, in the second step of the time, it will be corrected and the system will converge to the expected position. So let me get back to this proportional and explain again what was here. Okay, this was, yeah. So totally we show that the proportional derivative feedback control outperform to the proportional feedback when there is no uncertainty. So our result shows that the feedback control outperform open loop control system even if there is no uncertainty. And if our system is of higher degree, we should incorporate the derivatives to control for the oscillation in the system, okay? So the control rule should be adjusted with the respect to the, the process. If our process is more complicated, we need to have more complicated feedback, and the proportional feedback will not be efficient and will not be sufficient as well. Okay, so this is the end of my talk for today, and thank you. And this is the control that I assigned your comments is like that I have the audience feedback, and then I will receive your the feedbacks and improve my presentation again. And your feedback is a signal to my presentation. Yeah. Okay, thank you.